Okay, here we go. We are on board for the day. Okay. Except I wanted to pull up our worksheet again. Okay. So let's recap. Let's make sure we're all remembering where we thought we were. Okay. Last time we talked about 2's complement, right? We started off going one direction. We'll do the other direction today. But what was the general process? Let's make sure we all remember what we're doing before we keep going with new stuff today. What's the process of 2's complement? Right, we check is it negative, which means we have a 1 in which digit? Most significant digit, right? Okay, and the MSD or the most significant bit, whichever. A 1 in there means the number is negative, right? A 0 means it's positive. Or as you said, if we want to look at it in hexadecimal, what tells us in hexadecimal negative or positive? Right, so if we are positive, we are going to be 0 through 7. And if we are negative, we're going to be 8 through F, right? Okay, so we can look and see, is this number negative? All right, now what? Yep. If it's negative, we flip the bits. And then add 1. Okay. We flip the bits and add 1. What if it's positive? Then we just convert it like we've done before. Absolutely. Okay. So it's only negative numbers that need special treatment. All of our positive numbers are going to be handled as if they were unsigned. Okay. That's part of the beauty of 2's complement signed integers. Okay. Now, before we start going the other direction, I'd like to ask you guys a question. I might make you think for just a minute, but I have a short little discussion about this morning, okay? Obviously, in this class, and in life in general, we're looking for the whys behind things, right? We're looking for why things are the way they are. So let me ask you, why do you think it's important for you to learn 2's complement? I mean, we're spending an entire week on it this week. Obviously, that indicates some importance. So why do you think you need to learn something like this?
Used in the field somehow.
Okay, absolutely, it is used in the field. In fact, it's used in like 98% of the computers you're going to encounter are going to use it. Okay, good. What else? Why else would you want to learn it? What do you mean?
Like if you were trying to figure out how to set up options, but you didn't want to send it across in similar format. If you were setting across a binary, maybe think about this and like, oh, maybe I could set up a bit in front for a flag. Represent something.
Absolutely. Gives you ideas on how to encode different things in the future. Absolutely. Okay, good. What else?
Colors, maybe using colors.
Sure. Absolutely. When we want to do colors, where do you think the idea for colors came from? Good stuff. Same concepts, right? Or characters or anything else, right? Because when you get in the industry, oftentimes we think we're going to spend all of our day writing software, and we don't actually stop and think about what that means. Because we love to write code. I'm going to spend my days writing if statements and switches, and everything's going to be hunky-dory. Maybe a few functions and classes along the way. Okay, but computers or software in general is useless without data. Is that a true statement that you guys would agree with? Is a computer useless to us, modernly speaking? I mean, we can have a computer without data technically, but does the computer do us any good if we have it without the ability to store data? Not really, right? It's kind of pointless, okay? So if we need to store data, what are our options to storing data in a computer? Okay. Go even more abstract than that. Rather than not physical storage now, in terms of representing the data, maybe that's the better word to use. What are our options to represent the data? What can you use? Sorry? Binary. Okay. What's the only thing a computer knows? Ones and zeros, binary, okay? So let's say you need to represent colors. What's your choice? Ones and zeros, binaries. Is there any other option? No, and that's a good question, because oftentimes when we're working, if you've done CSS, for example, on the web, you probably encountered it there, or you've done, image manipulation, other things like that. Colors are often represented in hexadecimal, but who actually uses hexadecimal? We do, because what does a computer use? Binary, right? Hex is just another way of representing it. So you're going to get out there in the real world often to see the real world applications here. And you'll need to find either your own way to store something or interpret someone else's way to store something, okay? Let me give you an example. You guys want a story real quick this morning, okay? I was working in industry before I started teaching for a small little company called the U.S. Institute of Languages. And at this company, we wrote software to teach foreign languages. I like to describe it as Rosetta Stone that works, okay? If you've ever tried Rosetta Stone, you know what I'm talking about. They show you pictures and expect you to memorize everything from there, and it's very, very difficult. But our goal, we used a different method, was to teach people to speak the language of Spanish and then eventually expand into other languages. But at the heart of the methodology we used was, we had a lot of research that showed if you could show somebody animation and movement, especially if there was a little bit of humor, make that image memorable, it was easier for them to recall the vocabulary when they were out in the real world. So to do this, we had a library of approximately 30,000 GIFs that we sent out with our software to represent. I mean, they were just 3D animations with movement or something else, to represent the thing that was happening. Like a guy brushing his teeth with a shower head, or, just various things along those lines, right? We had these little 3D characters, and they would animate to represent the word. The problem we had was the language that we wrote our software in did not speak GIF. It could speak several other animation formats, but it could not speak animated GIF. It just didn't exist in the language itself. It's kind of like if you use Android. For years, it wasn't until just a couple of years ago, actually, that Android built in that ability. For years, you couldn't read GIF. It just didn't have the ability. It didn't know how to speak that language. Same thing with the original versions of iOS. Just didn't know how to do it, okay? Now, does that pose a problem for a company whose primary basis of doing their thing is built entirely on utilizing animated GIFs? Okay, so if you were in my shoes, what would you do? You've got 30,000 of these suckers that need to be displayed, but the programming language you're using doesn't support them. Okay, we could switch programming languages.
How far along? Yeah, that's the question. How far along were you? Is it feasible to change programming languages?
No. At this point, we're almost done. Change format? Okay, I could open each file and save it into a new file format, right? Which we started down. In fact, at first, we hired a high school intern, figured we'll pay some poor sap minimum wage to come and sit in front of a computer and open, save as, open, save as, open, save as. No, we couldn't. No. Because each of these files, when you open the GIF, the way GIFs are built is they're split into layers, and it stores the delta or the differences between each of the frames, which meant when they opened them in, they had to then do some manual adjustments before they did the save as for it to render properly. So on average, it took them between 15 and 30 seconds for each image, assuming they can go full speed the whole time. Never slow down, never get bored, never take a break, never get distracted, okay? Worst case scenario, let's say this. Let's do some math this morning, okay? Because you guys love math, don't you? Okay, let's say I have 30,000 images times. How long is it going to take my high school intern to convert my entire library? It's how many? 450,000 minutes. Okay.
That'd be 900,000 seconds and half of.
And then half that into minutes. Yeah. Okay. Now, how long is 450,000 minutes? That number doesn't even like, our brain just go, wow, that's big, right? Let's break it down into something that's more meaningful. Okay, how about hours? What if you divide that sucker by 60? Let's make it hours. Ish? Anybody got a 7,500? It seems a little small.
Yeah.
Well, you're dividing it by 6.
I guess that is true.
Technically, the other one should also be divided by 6. Now you have 30,000 times 30 seconds is how many?
900,000, and then there's, you cut that in half because each of them's.
Divide by 6 to get each minute.
Do we need to pull out a calculator and do this for you? Come on, guys. It's not that hard of math. It's right. Okay. So 7,500 hours, right? How long is that? Does that even like compute to you guys? Do you look at that and go, hey, it's what?
Over 300 days.
A little over 300 days. I'm going to just approximate that one. Okay. So I can hire a high school intern and pay him minimum wage for 300 days. In fact, when we ran our small scale prototype, we estimated the 30 seconds based on us doing it, right? We brought him in and we ran him for a week, and he had done a quarter of what we had anticipated him being able to do in that period of time.
Multiply that by 40.
So we were staring down the pipe of almost 4 years to do this conversion. Okay, so what do? Do we just bring in more high school interns and say, hey, let's bring in 3 of them or 4 of them and we're still back on target for a year? Is that a feasible solution?
There's no way to automate it.
Not like that, because there comes the real problem though, right? Because what is it that makes this thing expensive right now? The whole process is manual, so it's all about time, right? In fact, if you factored in 7,500 hours times, let's say minimum wage, about $8 an hour, right? What was the costs we were anticipating right here too? $16? 60? Like that? $60K to do this conversion. What do you think? Is that a wise expenditure of money?
Probably multiply that by 4 due to how fast they actually went.
Now you're looking at spending close to $250,000 to translate a library from one format to another. Good idea, bad idea? Yeah, so we came to the same conclusion, right? We tried it out for a week and realized this is horrible. It's never going to get done, especially when we looked at other content production schedules and we could see how quickly over time, especially highly repetitive tasks, their efficiency started to do this. And they got slower over time because it was just monotonous. I mean, when you think about it, when you guys do just horrible monotonous tasks, do you tend to get faster over time? Not really, okay? So we went back to square one. We couldn't change languages. We couldn't manually save as, and do all that process. Neither of those are feasible. What's left to do? We've got to figure out a way to do this in software, right? So we explored several options. Option number one was we could see if there was a package we could find that would automatically bring them all in and kick them all out. Unfortunately, one didn't exist, so we thought, well, maybe we could write one. But that's a lot of work and a lot of expenditure. By the time we did the process, we estimated that we would probably spend close to $150,000 in engineering labor to write the software. And likely we would be the only ones to use it. We wouldn't be able to recoup those costs by reselling it out onto the marketplace. Still a huge investment to make. So we came to our final and original, well, our final and best solution, okay? Which was the one you guys haven't said yet. Why don't we teach the programming language that doesn't support GIF how to support GIF? Except the library didn't exist yet, so we had to write it, okay? Now, what is it going to take to write a library like that? What do you need to know? You're too deep. We don't even need to worry about any of that crap yet. What did you say, Reese? There's one thing we need to know. The rest of the stuff we figure out as we write it, right? The only thing we need to know is how do we interpret the binary and what does it mean, right? We gave that a name last time. What did we call that? Context, exactly. The only thing we needed to know was the context. If I understand the context, what can I do with that context? Yeah, I can teach the software how to interpret it, right? Isn't that what you do, for example, anytime you open a file on your computer? What is it you're really doing when you open up Word and you go File, Open, here's my research paper, I'm going to open it. What is it really that it's doing? Yeah, it's reading those bits and interpreting them according to a particular context. So we thought, hey, let's spend a little bit of time and write a context interpreter. Let's write a piece of software that can speak GIF that can run, right? We'll write our own little library to bring this in, and then we can shove it out to the world at large. And other people actually used it a lot. And we found components that we could bring in from other places to build off of it, so we didn't have to build entirely from scratch. We found pieces and pieces and pieces, and we pulled them all together, and it took me a week. I spent 1 week of my time. Because I understood how computers speak binary and how we use binary patterns to represent data, right? Isn't that really what it came down to, is I needed to represent data in binary, or in this case, read data that was already represented in binary? 1 week. A couple of $1,000s. And I ended up saving the company, you know, if we would have gone the manual route, close to $250,000. Simply by understanding how computers store information. And this is going to be a critical skill, and I'm not exaggerating at all when I say that to you guys. And you'll see that come up over and over again throughout your education, and as you get out into the field at wild, right, at large, that the ability to see and understand how computers store information and then either design it or interpret it or both, right, is going to be something you're going to use on a regular basis. But I will warn you up front, you probably have noticed from last time, it's a little tricky, isn't it? Is it easy to make mistakes? Absolutely. And it's going to take time and it's going to take practice. So I really encourage you guys to take that time, especially, you know, working on those memorizations between binary and hex. I know it seems silly at first blush, right, to memorize that, but it will pay off dividends hugely in the long run when you can look at a display in hexadecimal and realize what that data means, right? The entirety of the reason we use hex is it shows us a lot of information very quickly, but you guys don't speak it on a regular basis. So you look at it and you go, hey, there's letters, numbers, whee, there's something there. Okay, but you got to learn to speak the language of a computer, which is why we're going to spend all of this week on that topic and all of next week, okay? Because it is crucial for you to learn to speak the language of a computer. Otherwise, as we start going into the architecture beginning in week 4, we're going to start at an electrical level and work our way up, okay, to programming languages at the end of the semester. Over that period of time, if you don't understand what language the computer is speaking, you'll never understand how it transfers data or why it transfers data the way that it does or why things are structured and built the way they are, okay? So really at the heart of a computer, even before we get to the CPU itself and its ability to process things via gates and transistors, even before then, logically, we have to understand how data is represented, okay? That's why I'm asking you to spend so much time on this week, because it'll pay off in the long run if you'll take the time to do it, okay? Can I get off my soapbox yet?
No, we still have hopefully another hour.
We got another hour and a half so until I can really get off it, right? Okay. All right. So, but hopefully that lets you see some practical application too to the value of learning these concepts. I mean, imagine you went to your boss and say, who's trying to figure out how he's going to swing $250,000 into this project that's already a year over schedule. And kind of having a small heart attack because we're a small company. I mean, there was like 8 of us in the company in total. And you go to them and say, hey, you remember that $250,000 you're going to spend? I can fix it. Give me a week, maybe 2. And we don't have to spend anything other than my salary. You can imagine his reaction, right? Yes! And he bought us pizza because as nerds, that's what we wanted. We wanted pizza and video games. So he bought us pizza and we played video games one day for lunch for saving him $250,000. You can imagine the fun that came, right? Okay. But all because we understood the contextual way that binary works, that by understand, if we can figure out what that binary pattern means, we can tell the computer to do anything, right? Okay, and this translates into lots of areas too. Imagine you are maybe you guys are interested in criminal justice, right? Or you watch those crime shows. Okay, for the record, when they pull out their magnets and they wave them over the hard drive to read it, that's totally BS. I watched that the other day on an old Castle rerun, and I almost fell over because I couldn't believe it. I'm like, no, they unscrewed the top and everything. Oh. So, but the ability, when they're looking for data that's hidden, right? Or spies, or lots of things like that, that's very common to hide data within the data, but you have to understand the context, whatever it is you're doing, to understand what somebody else is doing, okay? Speaking binary may seem antiquated and outdated, but it is a critical skill for the real world, okay? At least if you want to be the guy that's paid $150,000 a year instead of the guy that's paid $40,000 a year. You choose. The one that everybody comes to with their problems for solutions, or the guy that's always going to someone else for help. Okay, that really is going to be one of the key foundational pieces to launch you guys into a lot of success if you want it. Okay, so let's go the other direction now. Okay, let's see if we can figure it out. Let's imagine we have a number in decimal now that we need to figure out how to encode. Okay, so let's say we have something like 10,000, negative 10,256. That's a nice even number, okay? What do you know about 2's complement? How do you think we might go about this? Okay, we need to be able to see this in binary, right? Except, I mean, that's our ultimate goal, obviously, right? But to go completely into binary, we have one giant problem. What doesn't exist in binary? Negatives. So what might we want to encode into binary first then, if we can't encode a negative sign? Yes. So let's encode the absolute value, right? I.e. the distance from 0 of the number itself. Fancy words or unfancy words, like you said, was positive equivalent, right? Let's figure out how to put this bit into binary, okay? So what do you guys do? How do you put this into binary? What's your process? Let's use that middleman the way he's designed for, right? Let's drop it into hex. Because we could do it all in binary by figuring out, let's pull out a factor of 8192, and then let's pull out a factor, of all those little binary pieces, but it takes too long, right? So in hex, how many digits are you going to need? We're going to need 4, right? Okay. Okay, let's pull out how many factors of 4096, right? 16 to the third. You guys are going to want to break out your calculators again. Right? Okay. We can pull out 2, right? So if I've represented 2 in the box worth 4096, how much of this number have I represented? 8192. Okay. Leaving us how much left to represent? Okay. How many factors of 256 can we pull out? Okay. Representing how much? Leaving us a balance of? Then a 1 and a 0. I like to play with numbers. Did anybody catch what we did with that number? There we go. We got one on the back row. What's that? What class are you sitting in right now? Ba-dum-bum. A couple of you got it. It kind of fell flat, but you know, what are you going to do? Okay, so this represents the positive equivalent, 2,810, right, in hex. Okay. So I have the I have the absolute value of my number encoded. Now what do I want to do? Because our goal wasn't to put it in a hex, it was to get it into what? Binary. Okay. Correct? 2810. Okay. Now, here's where we venture into new territory, right? Okay. What was the mantra I asked you to represent or to memorize for 2's complement? Flip the bits and add 1. So, what do you think we might want to do right here? Flip the bits and add 1. Yep. Okay. Now, why are we adding 1 still? This is an important discussion for us to have this morning because what did we do going the other way?
Absolute value, and the other way you're still going 1 more away from that point of 0.
Right, because what was the reason we added 1 in the first place? Yeah, because 0 counted as what? A positive number. So that way our inverts stacked. A negative 400 was on top of a positive 400. They were equidistant from the limit, right? They were the same distance. Whether you want to look at those limits on the ends or the center, doesn't matter. The idea is they're the same distance away from whatever limit you're looking at, right? Okay. So we'll always add by 1, right? Because 0 is always a positive number. Okay, because it's always that positive number, we have to compensate for that so that we line up on top of each other. Now, it's very common. Okay, students will think, oh, we're going the other direction. I'm going to subtract by 1. Okay, and there definitely will be cases where we'll go both directions, where we'll add coming one way and subtract coming next way, as soon as next week even. Okay, but because 0 is always positive, make sense? All right, so we need to then do what before we can add 1? Flip the bits, and then we add 1, right? Okay. So what does that look like when I take these bits and we flip them? Here we go. 1 1 0 1. Yay, we're going to get to do math. Okay, we flip the bits, and then we add 1. Okay, because 1 plus 1 is 0, carry the 1, right? So that just kind of ripples along until we hit the 0, which then becomes a 1. Because we have 1 plus 0, and then everything drops down. Exactly. Oops. Except it helps if you drop down the right values, doesn't it? Okay, make sense?
So, if you were to start off by subtracting 1, which coincidence in this term that you remember?
No. Because that's a really great question, and we're right where we were going to go next. Okay, so we're going to put this number on hold for just a second, and let's look at that. Okay, so just to reiterate. Okay, so if I were to have subtracted 1 before I flipped the bits, I end up with the same result. Why is that? Okay, that's the question here. So when I take a number, let's say I have 0, 0, 0, 1, and I flip the bits, I end up with what? Oh, what do you know about it?
Not quite offset.
Yeah, we haven't compensated for the offset yet, right? Okay. What characteristics about it do you know? Is it positive or negative, for example? It is negative, right? Okay. So what happens if I take a negative number and I add 1 to it? Well, no, we essentially subtracted in this case, didn't we? That's why we can always flip the bits and add 1, because we're always adding. Because when you add 1 to the negative number, it's essentially subtraction, right? Isn't that what we talked about last time? A computer is always doing addition. Just oftentimes it'll use addition of a negative number to compensate for subtraction. It's the same concept, right? We always flip the bits and add 1, because by flipping the bits, we compensate for the times when we're adding 1 or subtracting 1, depending on what direction we need to go, because it's compensating for that in the flip, right? Because when we store these numbers, right, we start at 8,000, right? What was the equivalent of 8,000? Do you remember? If this was an 8,000 hex, what was that equivalent in decimal? Nope. Well, if we were to, that in binary, yes. And then we would flip and add 1, right? But if we were to convert this to decimal, what would it be? Yes, which was negative 32,760. Oops. 768, right? Okay. All the way through to the limit. Where's the limit? Well, that's the positive, which is 7 FFF. So that's on this side, right? The limit was F's, right? Because we keep counting up by 1. And what is FFFF? It's negative 1, right? Okay. So 8,000. What is plus 1 to 8,000? If we were to take 8,000 plus 1, right, gives us 801, right? What is this number in decimal? You don't even have to do the process if you stop and think about it. You can use logic. I'm going to let you deduce it. Bingo. Okay. Negative 32,767. Every time I add 1 on a negative number, what am I doing? Bringing it closer to 0, right? Okay. No. Which is closer to 0, 32,768 or negative 32,767? Yeah. Okay. So we always add 1 because by the flip, we compensate for whether those times when we need to add 1 or subtract 1. That's why, for example, if you subtracted and then flipped, you're going to end up with the same thing because you're doing the same process. You've just flip-flop the steps, right? Okay. Now comes into some of the characteristics we're going to need to talk about today. Okay. And I'll answer that just because you asked it. We're a little bit ahead of where we were going to go, but that's okay, right? So let's say we have a number called 8,001, right? We subtract 1 to this guy. Or yeah, so 8,000, sorry, and we subtract 1 from it. What do you have? We're doing math and hex now. 7F, F, F. Okay. Now, when you said 8,000, i.e., if we were to write the equivalent here, right, in decimal, 32,000 or negative 32,768, we subtract 1, what would you expect to get? Negative 32,769, right? Are these, where'd my pen go? Come on. Are they equivalent? This number is what? So therefore it means this number is positive. It is not a negative number. Sugar. Right? Likewise, what happens, and we'll give the names to these in just a minute, okay? What happens if we did something like this? F, 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 F plus 1. Assuming the constraint to 16-bit still. What is the result? Okay, this would be the same as us saying negative 1 plus 1, right? Okay, negative 1 plus 1. Does this one work? What's negative 1 plus 1? We're bending your minds now, right? So does this work? Why does it work one way, but not the other way? Pardon? They are in a loop. Exactly. Okay. We call this particular condition overflow. Okay. Because I have overflown the number of bits needed to represent a given value. Okay. Now this one works, negative 1 plus 1 works, because can I represent both of these options given this number of bits? Yeah, it fits, right? So I can do that mathematical process and arrive at the correct answer, okay? We overflow when I'm going too big on the decimal limit, right? So for example, what would happen if I wanted you to do this? Let's say I wanted you to store 32,769, for example. We overflow. Why do we overflow? For example, for clarity's sake, if you were to go through this process and do it all by hand, you know, the flipping the bits and adding 1, the answer you would end up with is that. But this is a negative number, right? So what happened? Why do we have a negative number from a positive number? We've exceeded our limit. We have overflowed the boundary, right? Think of it as a number line. Okay? Once again, one of the technical terms you thought you would never see again in the real world, right? Okay? We have 0 here in the center. Numbers extending to infinity on both ends, right? Except in 16 bits, we can't meet infinity, can we? Okay, what are our limits? If we were to draw lines here for our limits, let's put our limits on this number line. What are they? Yep. And a positive 32,767. What happens, in fact, let's change colors so you can see it. What happens anytime I step on this side or this side of my number line now? It's kind of like a mod. If you're to treat it as absolute value, unsigned integers, it really would be more like a mod. Since we've split the range positive and negatives, a full mod doesn't work, but that's the basic gist, right? Okay. We essentially do what? And work this way, right? What happens when I'm going on this side of the number? Where do I go? We go to the other way and work our way back through again, right? Because what would happen if I tried now to encode a negative 32,769? Am I going to get that number in 16 bits? No. Okay. We're going to get something that doesn't fit anymore. We are going to overflow our boundaries. Okay. Now, we're going to put overflow on hold for just a minute, finish that example, and then I'm going to make you guys actually convert this so we can talk about it, okay? So let's rewind just a minute and finish really quickly this example, okay? We were almost done anyways. We only had one step left. We're working on right here, right? We flipped the bits. We added one, and what's left? Look at it in hex, because that was our goal, right? So what is this in hex? Okay, so D7F0 is the same as what? Again? Negative 10,256, okay? All right, so I want you guys now, I just wanted to make sure we finished that off so you guys saw that all the way end to end. I want you guys to convert this one, negative 32,769, okay? Take a couple minutes and do that conversion real quickly, please. Okay, you guys done? Raise your hands if you're done. Okay, we got two. We'll give you a couple more minutes to finish. That's okay. All right, raise your hands if you're done now. Okay, that's a good majority. So, process we follow here, right? We need the absolute value of this number, yes? In hex. What was that? Do we need to actually write out all the steps as we do it? Sure, let's do it, okay? So negative 32,769, right? We need how many digits in hex? 4. Okay, so how many factors of, what was this number again right here? What positional value of this? 4096, okay? How many factors of 4096 can we pull out? 8, right? Which means we just represented how much from our absolute value, right? $32,768, yes? Leaving us a balance of, easiest math ever, well, second easiest math ever, right? Okay. How many factors of 256 can we pull out? How many factors of 16 can we pull out? How many factors of 1 can we pull out? 1, which completes our number, right? Because our goal is always to end with a 0 at the end. That's how we know we've done it right, okay, if there's nothing left. Okay? So, 8,001. Have we encountered a problem yet? Okay? No big deal, right? You sure? There's a problem here. Okay? The number we just represented was not this number, was it? Have we represented negative 32,769 yet? Because we haven't compensated for the negative side yet. We haven't flipped the bits and added 1 yet. True? This 8001 is the equivalent to a positive 32,769. But what's wrong? This 8001 is negative. This number over here, right? Should I circle it? Because you guys can't really see that dot very well. This number is positive. Okay, this is our first indicator they have a problem. But let's say you missed that and continued on. Okay, so we have 8001, right? Which, if we write it out in binary, an 8 looks like 1. Yep. True? Okay, now what happens if we flip the bits and add 1? So let's flip the bits. We end up with 0, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 0. And then add 1. Okay, what is this? Seven FFF. Okay. Is that equivalent then to negative 32,769? What do you guys know about 7FFF? It's positive. In fact, you know its value, don't you? What's its value? Yeah, 32,767. Is it 32,769? So what happened? How did I end up taking a negative number and resulting in a positive number? How did that happen? We wrap around the end, right? That was called a what condition? We've overflowed. Okay. We have exceeded the boundaries of our number, right? We tried to represent a guy that was like right here. Didn't fit. So we end up here, working our way backwards, right? Now, it just so happened to be that it landed perfectly on that border. If I would have given you something else, say 32,700, we would have landed a little bit farther in, right? Okay.
So for this question, what's the right answer?
Good
Do
question.
you say overflow or do you?
Well, if you were to do this process and do this conversion, right? What is it really that's causing the overflow? We got to go a little bit deeper down to get to the final answer, right? What is it that causes the overflow in the first place? No, the 2's complement. I mean, obviously we can store numbers bigger than this in a computer, so 2's complement itself is fine.
The number we started with.
No?
The amount of bits we limit ourselves to.
Yes. It's all about the bits. Okay? You can sing that in, oh, I just forgot her name. What's that singer's name? Dang it. The one that sings all about the bass. Meghan Trainor. Sing it in Meghan Trainor's voice and then you'll remember it. About the bits, about the bits. No overflow. Okay? You're welcome. You will now sing that for the rest of the day. It's kind of like when you hear that stupid You're Welcome song from Moana. It's been on my head for like months. I've got a 2-year-old daughter who watches it every day. Anyways, okay? So it doesn't fit because of what?
The amount of bits we limit ourselves to.
Yeah, so
32 and 64.
yeah. So if I want to represent 32,769, what do I need? I need at least one more bit, right? Because what happens to my range of values every time I add one bit? It doubles, right? So my range goes from 32,767 to negative 32,768, right? If I add one bit, that changes to a negative 65,536 to a positive 65,535 just from one single bit. Yeah, we have a 17-bit number. Now what happens to negative 32,769? It totally fits, right? We end up with a value that works. You just have to have another digit, don't you? Except nibbles now work in what value, in what sets? Groups of 4, right? So it does get a little bit trickier because this guy would either be a 0 or a 1 ever if I added only one bit. So our rule of looking at 7s and 8s goes out the window because 7s and 8s only work when I'm using the entirety of the nibble. That's why I keep emphasizing that it's important that we look at the content of the most significant digit, right? If it's a 0 or a 1, rather than simply just doing it in hex. Okay? Now, so what would be the answer here then? 32,769 in 16 bits. What's the answer? Overflow. Doesn't fit. Can't do it. Sorry. None of the above. Right? That type of a thing. Okay? Because it just doesn't fit.
So if you did need to store that number, instead of just adding a bit, wouldn't you just add another
So you would add another nibble if you wanted another hexadecimal digit. Yeah. Now yeah, well, it depends on your system. We can't always say easier because it depends on what it is you're doing, right? You know, in general purpose computing, generally we're going to add, it's either 16 bits, 32 bits, or 64 bits. That's like 90% of programming languages. Those are your 3 sizes you can pick from. Some of them will offer an 8 or even some of them will even offer a 1-bit value, Boolean, right? But let's say you're designing something a little bit smaller scale. Maybe you're doing an embedded system or robotics or you know, smaller scale hardware where the amount of bits matter more significantly. Then you may say, okay, well, I'm going to have 17-bit numbers. In fact, early computers were famous because they were 16-bit systems. And we had to figure out how to handle larger scale addressing. So we figured out how to squeeze 20 bits worth of information into it. And other tricks like that along the way. But yeah, so it depends in your general stuff that most of you are going to encounter. Yeah, you're going to double things because that's what we tend to do is we just double our capacities. Not always though. It depends a little bit on what you're doing though. Does that make sense? Okay, awesome. So yeah, in a normal computer, odds are you're going to be dealing with, I mean, most of the time when you guys declare an int, for example, in the majority of languages, when you declare an int, that is a 32-bit two's complement number for the overwhelming majority of ISAs out there. When you declare a long, anybody want to take a stab? Often 64. Now, for fairness, some languages use 96 bits. Depends on the language a little bit for that one. Okay, but that's where we're at. As you're looking at 32 or 64, sometimes 96. And there are some systems that go beyond that too, right? Especially some NoSQL databases will use 100 or even Oracle, for example, uses what, 124 bits for their long, I think it is a sequence. But anyways, that's neither here nor there. The idea is the concepts stay the same. It's just the math gets bigger as I throw more bits at it, right? Okay. In fact, let's take a little break, and just to show you that that is the case, we'll do one big one when we get back. Practice one with more bits. We won't go all the way to 32 because that's just gonna that would suck so horribly. But we'll take it up just a little bit, okay? So you can see the process remains the same. So go ahead and take 5 minutes, go get some caffeine, do some jumping jacks, run around the building if you need to. Had one student last summer whose favorite thing is to do is go outside and catch Pokemon. Apparently there's a gym outside. I don't know. I never got into that. So whatever, take 5 minutes and then we'll pick back up, okay? In fact, you probably remember that, don't you? You were in that class in 1010 over the summer. You were 1010 over the summer, right?
I wasn't in one of your actual classes. I was in, remember, it was the 2014, 2015 games competition.
Oh, it was game camp.
Yeah.
I was thinking that's why I put you with 1010 is because of games. I was thinking you were. Yep, that's right. It was game camp.
And we won.
Yeah. And we have game camp in June, and I have a brilliant idea I want to pitch to my team that I think will win.
You guys still using GameMaker, or you guys using like Unity?
Now, GameMaker. Unity has got too big of a learning curve to pick up in a week.
That's what I use now for most of my little projects. We're actually taking our game from game camp and redesigning it and making it better.
Boom. That's when you know you really won.
Yeah. We've already released one app onto iOS and Android, although we took it off of iOS because iOS sucks, and they charge you
Fair assessment, $100 a year.
$100 a year to keep the stupid app up there. It's only earning me $25.
Yeah, that doesn't make a lot of sense.
So we took it down off of iOS, but it's still on Android.
What's it called?
For the whole, app store security, Google, you can have it.
It doesn't actually change the security of the App Store, paying a yearly fee. Google, you pay a fee to get in too. It's just a once in a lifetime fee rather than an annual fee.
One thing, have you ever done any Windows Store development?
A long time ago.
Because you pay a licensing fee for that, and if you look at it on your account, it actually says that you have to renew it. You renew it in like, I think it was 30 years, like that.
Yeah.
So it's just, I'm assuming they just put just some arbitrary number in there.
They probably did because their existing systems were built around that concept. Interesting. That morning has rocketed by. I don't know if it has for you guys, but I feel like I've been talking for like 10 minutes.
Have you used C# before?
Mhm.
Have you used interfaces with C#?
Mm-hmm.
Okay, I've got a question for you then. Is there a way to essentially use an interface or maybe something else that you can say require a class that to have a function in it that you force to assign to a delegate? So essentially you're requiring that there's a function in there that is a delegate. I'm trying to set up a system using components so that I have, say, an active component that connects to my main class, but I have to know for sure that it will always have this function that can connect to it.
Well, an interface guarantees that the function's in place.
But it doesn't guarantee it's doing something.
Well, you can never guarantee that. The closest you could get would be by an abstract class. Because an abstract class, the difference between, do you know what the difference is between an interface and an abstract?
Yeah.
Yeah. So by providing default behavior, you guarantee the behavior is always present. It's just you pick what that default behavior is.
I'm trying to build a component system for that game, and I haven't quite figured out how I'm going to do it yet. Because anytime I try to do it, one half of it works, and the other half doesn't.
Yeah, I mean, there always comes at some point when you're coding out an interface, when you're designing an API, a code-based API like that, where you have to establish some level of trust between the implementer and the implementee. Where you say, here's my contract. If you want it to work, you fulfill my contract. So I can enforce you. You have to have this method so my stuff doesn't explode when I call it. I don't get a crash. But if they choose to leave it blank, honestly, that's kind of their call. Because the reason we're flexible like that is because people will figure out how to do things you never intended your API to do. And I mean, computers themselves, the only reason we have computers today in the form we have with PCs is because of people doing exactly that. Computers were never intended to go or become what they have become. It was hackers. People, which originally that term was meant to be, somebody who made something do something other than what it was originally intended to do. So those hackers bought computers and said, hey, I wonder if I could make it do this. It's not designed to do that. So I still wonder if I can make it do it. And they did. And then here we are. It exploded from there.
Now we have people still do stuff that things are meant for.
Yep. Except that is technically part of the HTML spec now. Not originally. Mm-hmm. Isn't it an exciting future? And scary. All at the same time. Anybody watch any of Google I/O yesterday? One of my colleagues described it. This will make sense because we're in Utah. He called it Google General Conference. It's their annual developer conference where they, get together and flaunt all their new stuff. But they released some new hardware yesterday that's friggin' amazing. It's called a TPU. You know how they have their...
Thing that is in the HoloLens?
No. Nope, this is entirely custom built. Yeah, so this is entirely built by... It's the same concept, though. Google has an artificial intelligence network that they call TensorFlow. They built these TPUs now, which are custom designed CPUs specifically built for machine learning. So their AI capabilities are going to scale astronomically in the near future. Creepy and exciting all at the same time.
Now it's some machines and chips in their heads.
Welcome to Skynet, my friends. It is here to kill you. All right, is everybody back? I think everybody's back now, right? All right, I'll stand back up then. It's just so comfy on that chair. All right, well, I better not draw on that screen with this. There goes a $4,000 monitor.
Don't they have, is it glass on the front of the screen? So you probably could erase it.
It's plastic. It may or may not erase. I don't know. We had a faculty member many years ago. To this day, still holds a legend. Everybody makes fun of him. He was got all, gets all excited and forgot he had his screen down and wanted to write something on the whiteboard, and the screen was over the whiteboard. Pulled out his marker and is out here just. Yeah, they had to replace the whole screen. You couldn't take it off with anything. Custodial services tried for weeks to clean it. Mm-hmm. Professor Hart. A lot of people, used to tease him about. You've heard it's like that blonde joke. Taking white out on the screen, to erase things. We used to give him grief. Anyways, I digress. Okay. So, excuse me, the Dr. Pepper biting me there. Let's look at one larger number just so we can see that it doesn't matter. And then we're going to move on to something else. Fair enough? Now, do you guys want to do both directions in a larger number or just one? I'll leave it up to you.
He's giving you a binary answer that's not one answer.
I have a binary response to a binary question. Which one? Okay, let's do both. You guys are, whoa, that was close. Okay, you guys are killing me today. I like it. All right. So, which one do you want to do first, decimal or hex? Start with decimal? Okay, let's start with decimal. I like it. Let's convert this process, okay? Sure, why not? Will 1 million fit in the number of bits of one of these? Hold on, let me do some math. Maybe. Let's do 500,000. This is your bank account, and you're getting ready to go buy a hypercar. Well, not a hypercar, I guess a supercar, because 500 grand won't buy a hypercar. It's the next level up. It's like a Koenigsegg, or like a Ferrari LaFerrari. You're going to spend a minimum, or McLaren maybe. Oh my heck! I love cars. If you can't tell. Anyways, for a hypercar, you're going to spend somewhere between $1 and $30 million, depending on the car. Crazy. Anyways, so $500,000. Okay. In fact, we better make it negative because you just spent it. Right? Okay. What's our process? We do what? Two things. We look at it in binary so that we can. Yes, but two steps. Come on. We've been repeating them all day, people. We flip the bits and add one. Always. Yep. Same thing. If it's positive, you just do a straight conversion. Yep. Negative, we flip the bits and add one. So we need this sucker in hex. We're going to need how many hex nibbles? We're going to say 5. Okay. Because our positions, 16, 0, 16 to the first, 16 squared, 16 to the third. Oops, I didn't put the fifth one up there. And 16 to the fourth, right? Which is what? What's 16 to the fourth? $65,536. Yep. That's why I didn't do a million, because if we would have done a million, we would have needed a whole nother nibble, and then the math just gets big. I only wanted to add one extra nibble rather than two. Okay. So how many factors of 65,536 do we fit here? Can we pull out? Right? If we have the absolute value here, which is 500,000, how many times can we pull out this? Say 7? Okay. Which represented how much of this number now? What's 7 times 65,536? Okay, leaving us a total of what on the back side? 200 and what? 48, thanks. Okay. Now, how many factors of 4096 can we pull out of 41,248? Okay. So 10 doesn't exist in hex, so we need to pull out A. Good. Okay. So A times 4096 is? Good one. That's an easy one. You don't even need a calculator for that one. 40,960, right? Just add a 0 because we multiplied by the base. All right. Leaves us a balance of? Okay. How many factors of 256? 1. Okay. We subtract 256. Leaves us a balance of? How many factors of 16? Pulls out and leaves us with 0. Right? 7A120. Now, what is this 7A120 equivalent to? Is that negative 500,000? That's positive 500,000, absolutely, right? That's these two. What the heck? I think does weird stuff sometimes. Okay, so to give a negative value, we need to flip the bits and add 1. All right, let's look at it in bit form. 0, 1, 1, 1, 1, 0, 1, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 0, 0. Okay? Which flipped becomes 1, 0, 0, 0, 1, 0, 1, 1, 1, 1, 0, 1, 1, 0, 1, 1, 1, 1, 1. Then we will add 1, right? You're probably noticing as you go, being careful is a good thing to do, right? Okay. 1 plus 1. Oh, carry the 1, right? Right. Guess I should probably not be lazy and write all the ones up there. Okay. Now, just as a pro tip for you guys, okay, as your numbers start bleeding together, I've had many students in the past who, to separate their numbers, will go like this. Why is that a bad idea? Looks like another one, and all of a sudden you're adding digits. Yeah, you're adding nibbles, okay? So instead, what I like to do is underline them. I've seen some students like go over, under, whatever, right? I just don't do lines. Okay? All right. So what do we have here? 8. 5. E. 0. Hex. 8, 5, EE 0 is negative 500,000. Right? Make sense? Yes? Okay. So you can see the process is exactly the same. The numbers are just bigger as we added more bits. Same thing happens when we go 32 bits, because how many bits is this? 8, 5, EEO. How many bits do we have? There's 20 bits, right? Okay, awesome. There we go. So that gives us 2.5 bytes, right? Because each of these together, that's 1 byte, that's 1 byte. So most of a byte. It's a nibble. 2 bytes and a nibble. About the size of a muffin. All right. Okay, let's go the other way now, shall we? Let's do one in hex. Yeah? Okay, we'll be quick. Let's do F. No, scratch that. E. F. 0. A. D. Okay, 20 bits again. So our process is to do what? 2 steps. Yeah, could we flip the bits and add 1, right? So in binary, to flip the bits, what's an E look like? 1, 1, 1, 0. An F. Yep, 1, 1, 1, 1. Zeros. How about an A? 1, 0, 1, 0, and a D. 1, 1, 0, 1. Yeah, because 1, 1, 0, 0 is a C. Yeah, because we take 1, 1, 1, 0 minus 1, right? Which meant I had to borrow this guy over to break him in half. All right. We have the bits. Now we are going to do what to them? Flip them, right? Let's flip them. 0, 0, 0, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0, 1, 0, 1, 0, 0, 1, 0. And then we add 1, right? Okay? Now we can either add up all those binary ones that are turned on, or we can flip it back into hex and do some simple multiplication, right? I'd say hex because it's a lot easier, right? So what is this in hex? 1, 0, F, 5, 3. Yep. Okay. Now what is this 1, 0, F, 5, 3? That is the what? The positive, right? So it's the absolute value of the number, right? Okay, because we've just removed the sign out. So it's the equivalent of that absolute value. So same process, right? Okay, let's multiply this out. We've got 65,536 plus F times what? Excuse me, sorry. 256, right? So F times 256, which is, okay, plus 5 times 16, which is plus 3, right? For a grand total of, right? Is that right? 69,454? Negative. Survey says we got 2 competing answers. What? 59? All right. Probably just a typo. All right. This time you bought yourself a Mustang instead of a supercar, instead of a Lambo.
Might be able to get a
Ooh, you could. That'd be cool. I'd be okay with that. You couldn't buy a new. You couldn't even buy the new Stingray for that, though. All right. Or you could buy one mother of a computer for 70 grand. We can have a lot of fun. Or what? Oh yeah, you could buy a Hellcat. Or we could buy a Hellcat and take its engine out and put it in a Razor.
What's a Hellcat? Is that a car?
Yeah, it's a Charger with their 700 horsepower engine. It's their answer to Shelby, like a Shelby Mustang, essentially. Yeah.
I'd rather have the computer. Computer's more useful to me.
All right. So do you guys feel comfortable, though, now with this concept of 2's complement, right? The idea of representing numbers now in this concept of binary and positives and negatives and all that stuff together. Is everybody okay with that? Okay. So let me give you a couple of tips. You got your quiz this weekend, right? Okay. Excuse me. Your quiz will be, for the most part, multiple choice, okay? But it is timed, as I said. So if you're doing conversions, you got to be fairly quick at it, okay? But again, what's our goal here? Hows or whys? Okay, I'll just leave that as that for your quiz, right? Focus on the whys, and you'll find that it's much easier, okay? Now, on Tuesday when we come in, we'll go through the quiz again, and I'll help you guys see some of those whys. If you're still struggling to see them all, that's okay, because it does take time. So we'll help do that a little bit in class too if you're still struggling to see some of the whys. But again, think about why these numbers are the way they are, and what does that tell you about their characteristics and their behaviors and those types of things, okay? Fair enough? All right. Now, are numbers the only thing we ever need to represent in a computer? Okay. What's the next logical thing you would do? If you were, thinking back in the original beginnings of a computer, you figured out how to represent positive and negative values. What's the next thing you would do? Letters, text, right? Otherwise, how would we have Zork? And all of those historically amazing games and things like that all come down to text. Now, when it comes to representing text, the original standard we used, okay, was called ASCII, American Standard Character Information Interchange, I think. Close enough, right? I'm not going to ever ask you, tell me what ASCII means. That's what Google's for, if we're honest, right? Okay. What matters is why do we use ASCII and what is it, okay? Now, ASCII is a standard way of representing text, and it has a couple of characteristics you should know, okay, that will help us figure some things out if we know these characteristics. For example, in ASCII, every character, okay, our characters are each 1 byte. Meaning they're how big? What's a byte? 8 bits, right? 2 nibbles. Okay? 8 bits. All right. Every character is 1 byte or 8 bits. So what does that tell you about the limitations of ASCII? We start thinking about whys now, right? Okay, we know it's 8 bits. What does that tell you about it? We are limited to a maximum value of 255, which means there are how many options? 256 options, right? Because remember, the number of things we can always represent is the limit plus 1 because of 0, right? Okay, so we have 256 characters, okay? Now, in the modern world, that's proven to be a problem, and there's an alternate standard we'll talk about in just a minute, okay? But at the beginnings of a computer, that was more than enough, because how many characters are there in English? 26, right? So we do uppercase and lowercase. Goes like a deck of cards, there's 52. Ooh, we still got a lot of room left, right? Okay. In fact, here's a chart. If we zoom in, here's the definitions of the abbreviations. This comes out of your textbook. This is figure 206, so it's in chapter 2, the 6th figure in chapter 2, okay? But here's the ASCII table. So the way it's built is essentially we take an intersection, right? By looking at what zone it's in and which one we're looking at. Somewhere along here, right? You guys are pretty familiar with finding things in tables like this, aren't you? Okay, so for like a letter D, right? Could we figure out the binary pattern to look for a D?
Which way does it go? Is it top one the first symbol? The rows the first.
Columns, then rows. So D. Huh? Column, row, row. It's like in life, most things we do is columns and then rows, but you know, it's like a database essentially, almost, right? It's a giant spreadsheet. But yeah, it's matrix. We're gonna get into those in a couple of weeks. Give me time. Okay. Now, do you need to worry ever about memorizing the ASCII table? At least not for this class. Okay. The concepts matter though, right? Okay. Now notice we've got lots of areas of blank space. And sorry, Taylor Swift, you don't get to write your name here. Okay. I got like 2 smiles. You guys haven't heard that? The Blank Space song by Taylor Swift is like one of her only good songs. Okay, we have to watch Swift-A-Mean on Thursday. You guys remind me of that? It's an awesome video, Saturday Night Live. Anyways, okay. All right. Totally lost my train of thought. Okay, why the blank space? Yeah. Because how many things are there to represent here, right? And again, we could have done like a nibble and a half and be more space efficient, but computers work better when they're broken on those even chunks, right? That's why we chose a byte, because computers are highly efficient at transferring a byte. Everything gets complicated when we try to transfer, like, say, 3/4 of a byte, for example, right? Okay, so we deal with things in bytes. These areas were reserved for future use, okay? In fact, there was quite a bit of trouble as computers expanded beyond North America, right? Because computers were primarily developed here and in England and a couple of places where we speak English. And there's not a whole lot of characters that we need to worry about, right? But anybody speak a foreign language in here? What do you speak? Okay, Spanish. Could you write every word in Spanish with this? No, you're missing quite a few things, aren't you? For example, in Spanish, you would need an ñ, or you would need your acute accents, right? Uppercase and lowercase for all of those. So we're missing some characters, right? Anybody else speak a different language? Wow, this is the first semester I've only ever had one person speak a foreign language. Most of the time I've got like a quarter of the class raising their hands. Let's say, for example, Russian, Cyrillic. It's an entire alphabet replacement. Does it fit in here? How about, let's Mythbusters. Let's go to Chinese or Japanese. And we use kanji now, where they have one character per word or sentence sometimes, right? Does it fit anymore? And there came a problem because for a while, we were still utilizing the ASCII standard, and companies would develop their own custom ASCII that they would use within their applications to give you more typing abilities, which then caused problems.
So for characters, the binary is kind of arbitrary. Like you could like see a binary, apply it, and figure out what character it was.
You'd have to look at the table, unless you memorize the table, absolutely.
But it's not like numbers, you can see that and figure it out. Arbitrary.
Yep. In fact, you'll see some of that as we get into digits later in ASCII, in assembler rather. All this stuff? These are called control characters. So extra stuff that's necessary to facilitate transmissions. You know, for example, like probably the one you guys use the most is these two. The form feed or the carriage return. That's when you push enter, it means go down a line. So characters that aren't visible that we need, you know, like tabs, carriage returns, shifts, controls, escapes, cancels, ends of transmissions, acknowledgements, you know, all those different little pieces necessary to that are behind the scenes, beyond just the simple letters themselves. That's what all that stuff is. Yeah, because when computers were initially designed, ASCII was the standard. So it was utilized for protocols, i.e. the transmission portions. It was utilized for text documents. It was utilized for input and output on the console of the machine. It was pretty much everything. So, yeah.
So why not have all the characters or all your different values all in one big block rather than separated like that with all the different white space?
It actually comes down to math for this. They utilize several math tricks so you can quickly isolate where you are in the table depending on what it is you're needing to do.
Oh, the one where the characters start.
Yep, looking at the most significant digit again. We could use that to figure out within that portion, right? So, but anyways, that's the general concept. We don't need to get too detailed in how ASCII itself works, just the general broad concepts, right? The big problem we ran into, though, is people were making up and sticking their own stuff in these different spots. What happens when people make up their own standards or modify a standard without universal agreement? It's no longer standard, yeah. Good luck reading it. Let's say I open your file that you wrote in your software uses your own version of ASCII, and I open it up in a different program. Are my results going to be the same? We're going to end up with weird garbage, right? Okay. So we eventually realized there's got to be a better way. We have a big problem. Okay. We need to do this in a different way that allows more storage. Okay. So in comes a new standard. Unicode. Okay. Now Unicode has several different varieties. Okay. Or a name you'll see oftentimes, Unicode's often abbreviated to UTF. Okay. Unicode text format. UTF, and there's UTF-8, UTF-16, and UTF-32. Yep. This is the size of a character. So in UTF-8, how big is each character? 1 byte, right? It's at 8 bits, okay? Every UTF-16. Where'd the 32 go? Did you guys just watch that thing disappear? What the heck? OneNote is possessed. Seriously, I draw a line up here and it erases it down there. What the heck? Anyways, okay. So 16 bits per character or 2 bytes, right? We commonly call that what? What was 2 bytes? Going back to last week, first day of class. Ooh, rewind. A word. Right. Okay. 32 bits or 4 bytes. Now, we didn't explain this one to you, so we commonly call this a... Wait, no, that's a D word. Sorry. There is a Q word, which is 64. Because it's a double-double or a quad. It's 4 words. Okay? All right. Now, why different sizes? Why do I have an 8 and a 16 and a 32?
Because you have, like you're just saying, the 4 languages maybe?
Yeah. Different languages are going to need different amounts of characters. And why don't I just say, let's go, everybody gets a 32 bits per character. And we're just going to standardize on the big one. Kind of like we did with IPv6. Everybody just gets the big one. Yeah. Let's say you have a simple text document here in English. I have 8 bytes, or 8 bits, 1 byte per word, right, for everything, versus 4, right? All of my file sizes are going to quadruple if I would have just standardized on the big one. So we give options so that you can choose how much storage you need based on what it is you need to store, okay? And that especially translates to when we store data at volume. I mean, imagine a database, right? Let's say you're Twitter, okay? You're generating millions of tweets per second at 160 characters a piece, right? So let's say, just for easy math, you're generating 160 million characters every second. Okay? 1 byte is 160 million bytes. No big deal. 4 bytes a character now, right? Do things change a little bit? I mean, we're 500 million characters per second, or bytes per second. Do you see how that scales to be a big problem depending on what it is you're needing to store? So we give options so we can choose for efficiency, okay? Because in 32 bits, we can store every character in every language known to man simultaneously, okay? It's just we're choosing to take 4 times the amount of space to store simple things as we are so that we can fit the complex things, okay? So UTF-8, UTF-16, UTF-32. Same general concepts. There's a table. We look for a binary pattern, and it generates a character. In fact, it looks like this. Okay, here's a UTF-8 table showing you various digits, right? Okay. Well, the characters themselves only ever consume the 1 byte at the end, as you can see. They're showing you these 0 zeros up front because the same table is capable of showing us 16 bits as well. It's just the website. The UTF-8 itself is 00 through FF. Okay, but for computer interoperability, we'll often add those 4. Okay, but in fact, we can even change that. UTF, though, supports various extensions of UTF. So there are different versions of UTF-8. For example, if you know you're going to just store English stuff, basic Latin will cover, English and Spanish and Portuguese and, those ones that are based on that character set. Or say, we're going to go to Russia. We need Cyrillic. We go to UTF-8, Cyrillic, and now we have all the Cyrillic characters stored in UTF. Right? or we can choose different ones, right? These are all, this is 8 through 32. So like if you wanted to see a 32-bit UTF-8, let's do, how about Mahjong tiles? That's a cool one.
What?
Yeah, oh, they don't render very well on here. Yeah, all the Mahjong tiles we can show up. Okay, but the idea is by looking at subsets, we can then also a little bit more uniformly control what it is we're storing. Or Arabian, that's a fun one. Oh, this font doesn't have Arabic letters in it. That's scrap. But anyway, you get the idea, right? By building out a table, we figured out, we applied meaning. We said, you see this binary pattern, it means this thing. You see this binary pattern, it means this thing. You see this binary pattern, it means this thing, right? That's always how we store data in a computer. Always. Doesn't matter what the data is. You see a pattern, you do something. It's the same thing even for machine instructions. The thing that tells the computer add, divide, subtract, move, copy, delete, format. You see this binary pattern, you do this thing, right?
There's something that designates the binary pattern as a letter, though?
Mm-hmm. ASCII or Unicode. That's what designates the pattern to be interpreted according to that standard, is when we do that, right?
Is there a bit in there?
You have to know the context ahead of time. So if I were to just open up and dump a random pile of bits out of memory, they'd be useless to you unless you could figure out what they mean. Now, there are techniques that forensics will use. For example, there's common patterns you start to see based on data being stored in certain types of things by looking for, statistics and repetitions and things like that you can oftentimes figure out after the fact what it was when it was stored. But if you don't know the context, it's just noise. Because a machine instruction looks exactly the same as a letter, which looks exactly the same as a number, which looks exactly the same as a pixel.
So they can take like a distribution of the bits or something.
Mm-hmm.
Figure out what it is.
Mm-hmm.
So it's like reverse engineering a lot of this in context.
Some degree, yes. Reverse engineering is a little bit easier because machine instructions share a relationship you'll learn about later on in the semester to assembly called the one-to-one relationship, meaning one instruction in machine code will equal one assembly instruction exactly. So you can always take it and reverse assemble it back into assembly. And then if you can speak assembly, you can then try and figure out how to put it back into a high-level language. That's what a reverse engineer does. Yeah. Or like those, for example, like an example, and then I'll let you go. Security researchers this past weekend with that WannaCry ransomware, they figured out that 22-year-old that stopped the majority of the outbreak. She did that they didn't reveal the gender, I guess, by reverse engineering. They looked at it in machine code, went backwards, followed the logic, saw the pattern that it was looking for, reserved the domain name because it was poorly designed, and stopped the thing by looking at that relationship between machine code and assembly. Yeah, it's cool stuff. Okay, we're done for the day. We will see you all on Tuesday, okay? Now, don't forget your quizzes due when? By Sunday at midnight. Don't forget it, okay? Now, also, just one last little request, too. As you're working through this weekend, it will help you immensely next week if you can continue to memorize it, or memorize if you haven't done so yet, the equivalence between binary and their hexadecimals, okay? That will really make next week a lot easier if you can do that. All right? Okay, see you Tuesday.